Problem number 4, 2621. I have a 12 volt battery and it has a capacitance of 60 amp hours. It has an internal resistance of 0.31 ohm and it takes 4 hours to charge it at 15 amps. It's a given. You get your 60 amp hours. Now here is one end of the battery. Here is the negative side of the battery, here is the positive side. Here is the 12 volts. Let's call this point B. Then here is the internal resistance of the battery, which you know. And then here is the terminal of the battery. So these are the only 2 points that you have access to. And now you're going to charge this battery. Well, how are you going to charge this battery? You are going to put in here a current. The charge current is given to be 15 amperes. Clearly, if you want to discharge the battery through some flashlight or something else, the current would flow in this direction and the battery would discharge. Therefore, if you charge the battery, you have to put the current in the opposite direction, which is exactly what I am doing here. And the question now is, what is Vc if I call this point C minus Va? So while I'm charging, what is this potential difference? Well, Vc minus Va is Vc minus Vb plus Vb minus Va. But this is 12 volts. And this is that charging current of 15 amperes times the internal resistance. You know I, you know Ri, you know 12, and so you find immediately that Vc minus Va happens to be 16.65 volts. And it shouldn't surprise you that you have to use a battery, because effectively what you're doing is you're going to, of course, attach a battery to here. With the plus side here and the minus side here to drive that current through this battery against its own will, so to speak. That this battery needs a larger EMF of 16.65 volts in order to charge up this battery, which itself will only deliver 12 volts, reason being this internal resistance. What is now the total energy that is supplied during charging? Well, during charging, the total energy, the total power I should say, that is supplied is the total voltage that I applied, which is the 16.65, times the total power, which is the 15. And if I did not make a mistake, I believe this is 250 watts, but you better check that. So this is the total power that is delivered to the battery during the charging. Now in 4 hours, which is 4 times 3600 seconds, the amount of joules that I pump into the battery is of course the time times the power, and that I found is 3.6 times 10 to the 6 joules. Almost a little more than 3.5 million joules. But now comes an interesting question under C. As I am charging, how much energy is dissipated in that internal resistance in the battery? Well, that is of course the time, which is the same as 4 times 3600 seconds, times the current squared through that internal resistance, which is your 15 amperes, times the internal resistance itself, which you also know is 0.31 ohms. And you find now that this is a huge amount. This is 1 million joules. So you put in 3.6, but as you put in 3.6 in the whole system, that means you put it both in the battery and in the internal resistance, 1 million of that gets lost in terms of heat of that internal resistance. Internal resistance gets hot and it's gone. You're heating up the universe. 1 million joules. So when the battery is completely discharged And I do that through a external resistor. Here is your Ri, here is your 12 volts, your terminals of your battery, and I'm going to here put now an external resistance, discharging this battery. And I'm going to discharge this battery at a current of 15 amperes. That's what you're being told. And it will take 4 hours because the battery has a capacity of 60 amp hours. So for 4 hours will this continue? Let's assume that the current remains constant, which is a little bit naive to think, because this value for our I will probably go up with time, but we ignore that for now for convenience. And now what we are being asked is, what now is this external resistance? Well, I would suggest that we use Kirchhoff's law. We start here, we go all the way around the circle, and then the sum of all potential differences, I will write that down in shorthand notation, going all the way around, must be 0 in this problem. Now I'm going to make an agreement with you. Whenever I go uphill, that means whenever I go up in potential, I call that plus, and whenever I go downhill, I call that minus. You don't have to do that. You can reverse this, and your answer will be no different. So I'm going to start here, and I'm going to go around counterclockwise. If you prefer to go around clockwise, it would make no difference. So be careful. The current comes to me. The resistances are external, so I'm going up in potential. The potential here is higher than here. Uphill is plus. So I get 15 times R external. Now the current here is also coming to me. So I also go from a lower potential to a higher potential. So I get plus 0.31 times the same 15 amperes. But here, now I go down in potential. And when I go down in potential, we agreed it would be a minus sign. So this is minus 12 equals 0. I know everything in this equation except this, and I find, I believe, 0.49 ohms. So that is now the external resistor. And now comes the question, how much energy is supplied to this external resistor during the discharge? Well, the discharge takes 4 hours. There you go. I must multiply that by I square R going through that external resistor times the external resistor itself. You know all numbers. And what do you find? 1.6 times 10 to the 6 joules. And now the question is, where's all this energy now? To charge it up, we needed 3.6 million joules. But while we were charging, we lost 1 million to this stupid internal resistor in terms of heat. And now we're discharging. And it seems that we lost another 1 million because we only end up with 1.6. Here, 3.6 went to 1.6. So where did this other 1 million go to when I was discharging? So what it comes down to is we lost 2 million joules somehow, and I would like you to tell me exactly when and where and how.